Okay, welcome back, and today we're going to cover the last topic of Chapter 12, which is going to be on confidence intervals for the true slope of a regression line. So just like we were talking about before, if we do a test for a significance for the rho, for the correlation coefficient, and we find that the correlation is significant, then that means that there is a true correlation in the population between the independent variable and the dependent variable x and y. So now if we're doing a regression, that means that there is a true regression in the population. So that would be represented by the prediction value that, hey, y hat is equal to beta 1 plus beta 2, or excuse me, beta 0 plus beta 1 times x. Now typically we use beta 0 as the intercept and beta 1 as the slope, but what we're going to do is, just because of this class, I'm going to use alpha plus beta x. Okay, so that's another way of using it. So alpha is the true intercept. Beta is the true slope of the regression line for the population. Of course, we don't know what this is, so what are we going to do? We're going to use our estimates, which is going to be a plus bx. Okay, so this video is going to be about how do we calculate a confidence interval for the true slope of the regression line, beta. So how do we do that? Well, so we're going to do a confidence interval for beta. And so the formula, again, you need two pieces, right? The anatomy of a confidence interval. You need your point estimate and your margin of error. In this case, we're going to use, it's going to end up being a t-distribution, so we can, it's symmetric, so we can use the plus minus, unlike with the chi-squared distribution that we saw earlier. So here we're going to have a margin of error that we're going to add and subtract from a point estimate. Well, what does this look like? Well, the point estimate is going to be B, right? That's going to be our best point estimate. B turns out to be an unbiased estimate for the true slope. So B is going to be our point estimate, plus or minus our margin of error. Now here's the margin of error calculation. It's going to be T alpha divided by 2 times S sub E divided by the square root of what? It's going to be this. Okay, it's going to be that. Okay, so now if you don't have a calculator, or excuse me, if you don't have the function that I'm going to show you in a minute, then you're going to have to use this formula. Okay, there's just no way around it. I'm going to show you how to use the calculator to make it easier, but you're going to have to use this formula. So you're going to have to remember this formula. And so if you don't have the function that I'm going to show you now, you have to know this formula. Okay. So now, the function on your calculator that will give you this confidence interval is going to be ln reg t int. Okay. And what you need to put into here, the three major things that you need to put in here is you need to put in your x list, okay? You need to put in your y list, and you need the confidence level. So again, this is going to be like L1, this will be L2, and then your confidence level will be whatever you want to put it in, okay? 0.95, 0.9, 0.92, whatever it turns out to be. And then once you hit enter or calculate, it will give you your confidence interval for beta. Okay, it's actually one of the outputs that you get. Okay, but if you don't, then you need to use this formula. So let's use an example. Okay, so with this example, we're going to use is this data set. Okay, so this is the data set that we used before, and it's the one that deals with yield. So it's going to be rain, annual precipitation in rain, in the inches, compared to the yield per acre. Okay, so that's the data that we've used before. So again, put this data into your calculator. The X list will be the rain in inches. The Y list is going to be the yield. So what are we trying to predict? We're trying to predict the amount of yield based on what? Rainfall. Okay? So again, enter that data in your calculator, and we'll go ahead and calculate this. So now, how do we do this using the formula first? Okay, well, once you have your data in the calculator, you're going to need these pieces, right? You need this, you need this, you need this, you need this, and you need this. So, and of course you need that. So I'm going to tell you where you're going to get those pieces of information, and then all you have to do is plug and chug. That's it. So now, the first thing I'm going to do is when I have the data entered into my calculator, I'm going to go to one var stats, because I need these three pieces of information. Now obviously we can get that from the data because we can count, but all three pieces are going to come from one var stats. So one var stats is going to give us so the sum of x, the sum of x squared, and n. So n equals 9, obviously. The sum of x is going to be 112.9, and the sum of x squared is 1531.39. Okay, so we've got those three pieces. So the next thing we're going to do is we're going to go to ln reg t-test. So ln reg t-test, so stat tests, and we go down to, so ln reg t-test is going to give me my S of E, which is S in the calculator. So under ln reg t-test, S is my standard deviation of the errors. Okay, and that is going to be 3.529. And B, my estimate, is 4.379. Okay, so now the only thing I need is my T alpha divided by 2, but that comes from the confidence level. Let's say we want a 95% confidence interval. Right, let's just use that. So obviously my T alpha then, alpha divided by 2, alpha, right, this implies that alpha is going to be equal to what? 0.05, and alpha divided by 2 is 0.025, right? So what's the function I'm going to use? I'm going to use inverse T, right? Just like before. So you should know this already. So inverse T, my area to the left is going to be 0.975. My degrees of freedom. Now here's where you have to use degrees of freedom n minus 2 because we're dealing with regression analysis with two variables, right? So two data sets. So it's going to be 7. And so in this case, our T critical value is going to be what? Well, let's go to second distribution, inverse T. And we get, what? 2.365. And now we've got all the pieces we need to calculate our confidence interval. Okay? So here's the thing. Here's our beta is 4.379 plus or minus what? It's going to be 2.365 times our S sub E, which is 3.529, divided by the square root of what? It's going to be 1531.39 minus 112.9 squared divided by 9. Okay, so that's what we have. So that's what I'm going to put in the calculator. And so now I'm going to get 4.379 plus or minus, so I'm just going to calculate this out. So 2.365 times 3.529 and divide that by the square root of 1531.39 minus 112.9 squared divided by 9. And what do I get? I get 0.778. So I get 0.778. And so my final confidence interval for the true slope of the regression line is going to be what? It's going to be this. So I get 3.600, comes out to 3.6 exactly. And now if I do 4.379 plus 0.778, I get 5.157. And so now this is my 95% confidence interval for the true slope of the regression line. So what do I get? I know that I'm 95% confident that the true slope in the regression line, in other words, we're talking about what? We're talking about the change in what? The change in yield, right? Bushels per acre for a 1 inch increase in annual rainfall, okay? So I know that with a 95% confidence that the bushels for every inch of increase, in rainfall every year, that the true number, the true yield is going to be somewhere between 3.6 bushels per acre and 5.1 bushels per acre increase. Okay? So again, for every inch of increase in rainfall, the increase in the yield is going to be somewhere between 3.6 bushels per acre and 5.157 bushels per acre. And that's the interpretation. Now, that's using the formula, okay? If you don't use the formula, if you have the function, so this is if you don't have ln-reg t interval in your calculator. If you do have ln-reg t interval, then that's all you have to do. So we can just ignore all this, right? And we can just use ln-reg t int. And so if we use ln-reg t int under stat tests, and it asks you for your two lists, it asks you for your x list, your y list, frequency, we're not going to touch, confidence level, 0.95, and then your regression equation, if you want to store your regression equation in one of your functions, like y1, y2, and then go down and calculate. So again, the only major things, only required fields you need to put something in is your x list, your y list, and your confidence level. And so now, what do we get? We get this. 3.6013 and 5.1569. So extremely close to what we got with the formula. So again, whether you use ln-reg t interval or if you have to use the formula, you'll get the same answer. Okay? So just be aware of that. Let's see here. Just want to test something. Okay, so other than that, that's it. Now, one thing I didn't talk about that I want to talk about now is S of E. Okay, what is S of E? Why are we using that in the formula? Because S of E, remember the residuals. Remember when we talked about we talked about unexplained variation in the beginning when we talked about regression, the least squares regression, and we talked about residuals. Well, what's the residual? Well, residual, if you remember, is equal to the observed value minus the predicted value. Okay, this is the residual. Well, the notation for residual is E. Okay, so that's E. So S of E is the standard deviation of all of the residuals. Okay, so again, we're assuming a couple of assumptions, like when we do regression, we're assuming the normality assumption and we're dealing with constant variance assumption. And so if those hold, then we can find the standard deviation of the residuals by calculating each one of the residuals and then calculating the standard deviation of those residuals. Okay, and how do we calculate that? By using this formula, which looks very similar to the formula we use for the standard deviations for any data set, like X, that we've been doing all semester. So the standard deviation of the errors is exactly that, what we would expect. It's going to be the sum of all of the squared residuals, right? In other words, it's the unexplained variation, right? So this is our unexplained variation, which is the sum of y minus y hat squared. Okay, and also this, I'll tell you what this is also called, but this gets into a little bit more technical. But again, we're going to divide by n minus 2. Again, the degrees of freedom. Okay, so this is the standard deviation for the errors, and also this is the same as the square root of, you'll see is what we call SSE over n minus 2. Okay, SSE is the sum of squared errors, right? That's what this is, the sum of all the squared errors. Okay, the residuals. Okay. So again, that's what we're talking about, and that's where it is. And on your calculator, whether you use linreg t-test, or if you use linreg t-interval, both of those will give you S. The S that is the output for either one of these is your S sub E. Okay. So other than that, that's about it. That wraps up chapter 12, and so next time we're going to start chapter 13, which is the last chapter, and that's going to cover a new topic, which is a new distribution. We're going to talk about the F distribution and how we use the F distribution to test for the difference of variances or population standard deviations, and also how we use the F test to do something called an ANOVA test, which is the analysis of variance. So we're going to talk about that next time. Thanks. Have a good day. Welcome back. And today we start chapter 13. And so in chapter 13, we're going to talk about a new distribution called the F distribution, because sometimes we would like to compare population variances instead of population means. For example, maybe a college would like to compare the grading of two different professors, and they would like to the variation in the grading process to be the same. Or let's say we're looking at a manufacturing process where the lid, right, that goes on the jar that they're manufacturing, they would like the lid to have the same variation in the diameter of the lid as far as, you know, the container, okay, to those two variations to be the same. Or we'd like to look at the variation between, what is it? Checkout times for two lanes. So you're dealing with multiple lanes, and they would like the variation among the lanes for checkouts to have the same variation as far as speed. Okay, how long it takes somebody to check out at a supermarket. Okay, so those are examples where we would want to compare either the variances or the standard deviation. So that's where the F test is going to come in, because we're going to be with two variances that we're going to be comparing. So what is the F test, and what is the F distribution? Well, the F distribution is a new distribution that is actually built off of two chi-squared distributions. So if you take one chi-squared distribution and you divide it by another chi-squared random variable, so we're talking about two random variables, right? So we have one random variable that's a chi-squared random variable. Chi-squared, let's call that chi-squared with V1 degrees of freedom. And we divide that by another random variable that's a chi-squared random variable with V2 degrees of freedom. And what we find is this is going to have a new distribution, which is what we're going to call the F distribution, where the degrees of freedom is going to be V1, comma, V2. And so we have the numerator, degrees of freedom, comma, the denominator, degrees of freedom. So how do we derive this? Well, very simply, it comes from the fact that we're comparing two sample variances along with their corresponding population variances. And so the F statistic is going to be determined by the two random variables. And so it says, suppose we sample randomly from two independent normal populations, and let sigma 1 and sigma 2 be the population variances, and S1 and S2 be the sample variances, or S1 squared and S2 squared. So we're going to deal with sigma 1 squared and sigma 2 squared are the population variances, and S1 squared and S2 squared are the sample variances. And then, of course, let the sample sizes for each one of those be N1 and N2, respectively. Since we are interested in comparing the two sample variances, we can use the F ratio. And the F ratio is going to, again, based on what we just talked about. And so what we're going to do is we're going to take S1 squared divided by sigma 1 squared, and we're going to take that ratio and divide it by the ratio of S2 squared divided by sigma 2 squared. And so this is what we're going to call our F statistic. Now, the F has the distribution that's similar to chi-squared, but the degrees of freedom, but there are two degrees of freedom. So again, we're taking two chi-squared random variables. So again, what we could do is we could expand this, and we could actually write it this way. N1 minus 1 times S1 squared divided by sigma 1 squared. Okay, so this is where the chi-squared random variables come from, divided by N2 minus 1 times S2 squared over sigma 2 squared. Okay, so that's where this is derived from. So we take two chi-squared random variables, and we can get this. Now here, this is the assumption that, well, if we have the same sample size for each one. Let's see here. What else would I like to say? Oh, the assumptions. So here are the two assumptions that we need to make. The first assumption is that the populations from which the two samples are drawn are normally distributed. So again, just like with the two chi-squared distributions, we always assume normality, that the populations, the values of the population X are normally distributed. The two populations are also independent of each other, so we're not dealing with dependent populations. They're independent of each other. Okay, let's see here. So it says, unlike most other tests in the book, the F test for equality of two variances is very sensitive to deviations from normality. So just like we talked about with the chi-squared distribution, these are assumptions that we are going to assume are met. And again, in real life, we test to make sure that these assumptions are valid, because any deviation from the normality assumption will wreak havoc on the reliability of our tests. Okay? So again, this is not what we call a robust test. Okay. Let's see. So let's see here. Okay, so here are the characteristics of the F test. 1, all F values are greater than or equal to 0, just like the chi-squared distribution. The degrees of freedom are N1 minus 1 and N2 minus 1. The curve is non-symmetrical and skewed to the right. There is 100% of the area under the curve, so the area of the curve will sum up to 1. The notation for f is going to be this. You can also use, you can see it here, you could use f with parentheses n1 minus 1, comma, n2 minus 1. But again, the typical one is to use f with the subscript v1 and v2, where v1 is equal to n1 minus 1, and v2 is equal to n2 minus 1. So again, the numerator degrees of freedom versus the denominator degrees of freedom. Also, mu, this is interesting to note as well. The mean of the distribution, mu, is equal to the degrees of freedom of the numerator divided by the degrees of freedom of the denominator, minus 1. So it's going to be v1 divided by v2 minus 1, which does not look right to me. It seems like there's a, I'm going to look that up just to make sure there's no error here. But mu is going to be v1 divided by v1 minus 1. So mu, the average, is going to be around 1. So keep that in mind. So what else? Is there anything else I want to say? Now, how do we find critical values? Well, to find the critical values, we're going to use an F chart. Okay, so we're going to find. Hold on, make sure. The critical value. Okay, so again, here are some of the curves. So again, it represents a family of curves. So here are some of the curves based on the degrees of freedom and sample size. So again, very, very similar to what you might see with the chi-squared. So when they're really small, it'll look like an exponential of some sort. And as the sample sizes get bigger, you get something that's unimodal and skewed right. Okay, so just keep that in mind. Let me see here. Okay, so now critical values. Critical values are determined, or excuse me, the F statistic first. So when we get to the testing, we're going to have our F statistic, F star. F star is going to be found by using the F ratio. Because what we're going to do is, for the null hypothesis, so in this case, if you look at the null and alternative hypotheses, so remember, our null and alternative hypotheses are going to be either this, and again, whether we use the variances or whether we use standard deviation is dependent on the problem. I'm going to use variance here, but again, if the problem is talking about standard deviation, we would just use standard deviation. But the hypotheses, again, are going to be the same. The tests are going to be the same. Okay, so these are the three sets of hypotheses we could have. Okay, so now notice in each one of these, the null hypothesis is what? We're going to assume what? That the variances are equal. So under the null hypothesis, what happens to our F ratio? Our F ratio, which again is this, right? S1 over sigma 1 squared, so S1 squared over sigma 1 squared, divided by S2 squared over sigma 2 squared. Well, if we're going under the assumption that the null is true, well then what happens to these two variances? They fall out. So what do we end up with? We end up with S1 squared divided by S2 squared. So this is going to be the formula for our test statistic when we're testing the variances or standard deviation, okay? So keep that in mind. So this is going to be the formula for a test statistic. Now, how do we find our critical values? Now, the critical values, we're going to have to use the F table. And again, just like we did before, it's going to be the critical value that basically determines our rejection region. So whether it's a left-tailed test or a right-tailed test or a two-tailed test. So the thing that we need for critical values is this. So we're going to need to find our F critical value, which is going to be alpha, right? Our chi-squared alpha, if it's a one-tailed test, comma V1, comma V2, because the 2 degrees of freedom are going to be involved. Okay, so we need to know alpha, and we need to know our 2 degrees of freedom. Okay, so here's the thing: we need to know 3 things. We need to know either alpha or alpha divided by 2 if it's a two-tailed test. And we're also going to need to know our degrees of freedom of the numerator. And we need to know the degrees of freedom of the denominator. Okay? So in the table, when we look up the F table, we have to find, first of all, what alpha level we're using. And then once we find the page, because each table has a different alpha level. So once we find the page of the F table that has the alpha level that we're looking for, then one column is going to be the degrees of freedom of the numerator, and the other margin, or I should say margins, one margin will be the degrees of freedom of the numerator, the other margin will be the degrees of freedom of the denominator, and then that's how we're going to find our critical value. Okay, so I'll show you an example of what that looks like in a minute. Okay, now that's how you find the chi-squared, the FR value. Okay, you're going to use the table. Well, how do we find the FL? FL, because all of the tables give you FR. If you want FL, is you're going to use the same charts, but whatever you find, to find the left, it's going to be the inverse of the right. So it's going to be 1 over FR. Okay? So keep that in mind. So the table will give you the right critical value. If you want to find the left critical value, you take the one you got from the right and take 1 over that. And that's going to give you the left critical value. So just keep that in mind. So let's see here. Now, here's what we're going to do. We don't need to use the chart because we're going to use a function on your calculator. The function on your calculator is the 2-sample F test. So 2-sample F test is the function you will use that will give you your F star value, and it will also give you your p-value. So again, we can just use the p-value and use the p-value method. Okay? So again, well, everybody should have the 2-sample F test on your calculator, whether you have a T83 or TI-84. Okay? So just keep that in mind. So once we do the 2-sample F test, and of course, all we're going to do for the 2-sample F test is we're going to put in the values from the problem, and then we're going to just use the p-value. Okay, so let's do this. So it says, 2 college instructors are interested in whether or not there is any variation in the way they grade their math exams. So let's say they teach the same class and they give the same exams. And they want to know, hey, is there any variation in the way they grade the same exams? So let's say they grade each other's classes, for example. I'm just throwing this out there. So let's say they take exams, right? And they take this one exam from this class. Let's say of 100 students. And what they do is they make copies of each exam, of the exams. So each professor has the exams for the students. And so they both grade the exams. They're wondering, hey, is there any variation in the way they graded them? Okay, well, let's find out. So they each grade the same set of 30 exams. The first instructor's grades have a variance of 52.3. So let's say first instructor, and we have the second instructor. Okay, so that's what we have. And the first instructor had a variance of what? 52.3. And the N1 in this case is 30, right? In fact, the sample size is the same for both of them, right? The second instructor's grades have a variance of 89.9. So S2 squared is 89.9. And N2 is equal to 30. Now notice something here. Which one has the larger variance? We want to test the claim that the first instructor's variance is smaller than the first instructor, or excuse me, the second instructor, or the second instructor. So here, what we want to test is we want to test the claim that the first instructor variance is less than the second instructor's variance, okay? Now, in most colleges, it is desirable for the variances of exam grade to be nearly the same among instructors. So we want to test this at a level of significance of 0.1. So in this case, alpha is going to equal to 0.10, okay? And our claim is that sigma 1 squared is less than sigma 2 squared. That's the claim. So in this case here, the claim is the alternative. Okay, make sense? Okay, so now, how do we set up our null and alternative then? It's going to be this. So sigma 1 squared is greater than or equal to sigma 2 squared versus sigma 1 squared is less than sigma 2 squared. And this is the claim. Okay. So this is a left-tailed test, right? Oops. So it's a left-tailed test. Now, the thing is as far as our steps, we're always doing the same thing, right? Step 2 is we're going to assume that there's no difference. So sigma 1 squared is equal to sigma 2 squared, right? And of course, that makes our test statistic just the ratio of the two sample variances, okay? Now, here's what we're going to do. Three is alpha is equal to 0.10. S1 squared is equal to 52.3. And N1 is equal to N2, which is equal to 30. And S2 squared is equal to 89.9. Okay? And so now, that's the information we're given. That's all the information we need. And of course, this is going to be an F test anyway, right, because of what we're testing. So this is step 4. We're going to use the 2-sample F test, right? And then, of course, what do we get with that? Well, here's where we're going to put in the data, right? So on here, when we do the F test, it's going to ask us for data or stats. So in this case, we're going to put in data. Okay? So now, here's what we're going to do. So we go to stat tests, and we're going to go up to the 2-sample F test. We're going to choose statistics, stats. Now, SX1 is, now here we have to put in the standard deviation. So we're going to have to square root those numbers on the board. So be careful. The calculator wants standard deviation. The problem gives us sample variances. So we're going to just square root those. So again, you just stick the square root in the calculator. So I'm going to put in the square root of 52.3. And then hit enter. And then N1 is 30. And then S2 is going to be the square root of 89.9. Hit enter. And then N2 is also 30. Now, the alternative hypothesis here is that sigma 1 is less than. So we're going to use less than sigma 2. So I'm going to select less than. And now calculate. And now my F statistic is less than 1. So my F statistic is less than 1. So F star will equal 0.5818. And my p-value is equal to 0.0753. Okay, so there are my two values. Okay, so here's the thing. Now, it's a left-tailed test, which means that if I want to compare this with the traditional method, then I would compare this with F sub L, which is going to be 1 over my FR value, which would come from the table. Okay? So I would take the inverse of whatever the right, because remember the F table, and I might have said this in class, but typically you want to put the larger variance on top. Why? Because that way if you use the traditional method, you can just use the F, whatever the value on the table gives you, and you're done. Okay? But in reality, it doesn't matter which one goes on top. It doesn't, because when you use the calculator, it's either going to be a right-tailed test or a left-tailed test or a two-tailed test. So again, if it's a left-tailed test, if we were to make this population 1 and population 2, well, then the claim is that this instructor is less than this instructor, which gives us a left-tailed test. But if we switched the populations and made this S1 and this S2, well, then it would be S1 is sigma 1 is greater than sigma 2. And it'd just be a right-tailed test, and you'd get the exact same p-value. So again, just like when we dealt with two populations before, it doesn't matter which one you make population 1, which one you make population 2, as long as you do the correct test. Okay? So again, it doesn't matter when you calculate the F statistic, right? When you calculate F star by hand, it doesn't matter which one you put on top and which one you put on the bottom. Typically, we do S1 squared over S2 squared, but as long as you are consistent with whichever population 1 and 2 are, and you do the right alternative hypothesis, you'll get the same answer. Okay? So just keep that in mind. I hope that makes sense, but just follow the way we did it. Okay? And so again, this is the left-tailed test, so we're going to compare this with FL. But again, we could just use the p-value method and compare it to alpha. So in this case here, p-value is equal to 0.0753, which is definitely less than alpha equal to 0.10. And so what's the result? We are going to reject the null hypothesis. So there is strong evidence to support the claim that the variance in grading for the first instructor is less than the variance in grading for the second instructor based on an alpha level of 0.1 and the sample data. And that's it, guys. So that's how you do an F-test. So again, watch the video, go through this, and make sure you understand how to do the test, and why the test works. Okay? So again, whether it's a right-tailed test or a two-tailed test, you're going to do the same thing that we've been doing for the chi-square tests or anything else that we've been doing. Okay? So now, let's see what else I can do here. Okay. We can also use this data. So let's use this data here. So here we have this data, and I'll explain what this data is in a moment, but let's say we have the tenor versus base. Okay, so population 1 and population 2. Okay, so pause and write down this information for this example. And so what we're going to do is, it says the New York Choral Society divides male singers up into 4 categories, from highest voices to lowest. So there's tenor 1, tenor 2, bass 1, bass 2. And in the table are heights of men in tenor 1 and bass 2 groups. One suspects that taller men will have lower voices, and that the variance of heights may go up with the lower voices as well. Do we have good evidence that the standard deviations of the heights of singers in each of these two groups, tenor 1 and bass 2, are different with 10% level of significance? So we're going to use that table. So these are heights of the men. One group is the tenor 1 group, and their heights, and the other one is the bass 2 group with their heights. So using that data, so what we're going to do is, the first thing I would do is I would put list 1 as the heights for tenor 1. And I would put L2, and I would put the data, so this is the data. I would put the data for tenor 1 heights into L1, and for bass 2 data into L2. That's the first thing I would do. Now, with the null and alternative hypotheses, well, what are they claiming? They want to say, is there good evidence that the standard deviations of the heights of the singers for each of these two groups is different. That's what they're looking at. So in other words, it's going to be the standard deviation of 1 is different from the standard deviation of 2. Okay? So are they the same or are they different? In this case, we're using standard deviations. Okay, so here is the null and alternative hypotheses. This is the claim, right? Are they different? Is the standard deviation of heights of men in the tenor group, tenor 1 group, significantly different than the standard deviation of the heights of men in the bass 2 group? Okay, that's what we're doing here. Well, which one is going to be population 1 and which one's going to be population 2? Well, it doesn't matter, but let's make this population 1, and make this population 2. Okay? So that's what we're going to do. So now, so just like before, step 2 is we're going to assume there's no difference. Okay? And then step 3 is, well, what data do they give us? Well, they give us the data here, right? I'm not going to write it down, but that's what I would do. I would put an arrow to 3, and then here our alpha level is what? It's going to be 10% again, I believe. Yep, 0.10 again. So based on the data and on alpha level, we know we're going to do an F test because of the hypotheses. So step 4, again, is going to be a 2-sample F test. And this time, we're going to use the data option, right? And then we're going to put in L1 for one list, L2 for the other list, and then the only other thing we need to put in is our alternative hypothesis, which is going to be not equal to, because it's a 2-tailed test, right? So we're going to do not equal to sigma 2. Okay? Now, that's all we need to put in, guys. Now, once we put in the calculation and we calculate this, what we're going to get is the following. So our F star value is 1.489. 1.489, which is very close to 1. Okay? So probably we're not going to reject. Our p-value will tell us immediately. So our p-value is 0.3430. So now we know the answer. So based on the p-value method, we will fail to reject the null hypothesis. So 5 p-value, which is equal to 0.3430, is not less than alpha, which is 0.10. So therefore, we fail to reject the null. And so now, at an alpha level of 0.1, there is not enough evidence, right? So we fail to reject this, which means, we fail to reject this, which means that there's not enough evidence to support the claim. So at an alpha level of 0.1 or 10%, there is not enough evidence to support the claim that the standard deviation of the men in the tenor 1 group and the standard deviation of the heights of men in the base 2 group are significantly different. And that's it, based on the sample data. And that's it, guys. So that is the way you use an F distribution and an F test to test and compare population variances or population standard deviations. And next time, we will talk about one-way ANOVA and how we're going to use the F distribution and variation, variances, in order to test the difference among means of multiple populations, meaning more than 2. Talk to you then.